Hey everybody, I'm here in my garden. That's a tomato plant. Today we're going to talk about solids one more time, but we're going to incorporate the idea of ionic solids. Everything up till now has been an element or a metal, and so all the spheres have been the same size, but when you have ions, the ions are different sizes. Remember, cations are smaller than anions, and they can be present in different ratios. So for example, sodium chloride, the ratio would be 1:1, and the number of atoms in a unit cell would reflect that. But also, something else could occur, like calcium fluoride, for example, would be CaF2, and there would be a 2:1 ratio of atoms, ions I should say, and that should be reflected in the number of atoms in the unit cell, but also the number of things in proximity with a particular ion, which they call coordination number. And then after that, we'll join the wonderful world of solutions. And so let's go talk about that now, and I'll get this tomato plant out of my head. Howdy folks, howdy. Mike here. We're back and we're going to talk unit cells and solids one more time, and you've done great to stick with it this far. Good on you. So what I did is I took a ionic cell problem. So I kind of dreamed up this. Actually, this is a pretty standard problem. You'd want to talk about sodium chloride. It touches everybody's life. Sodium chloride, okay, so I'm going to read this like a computer. Sodium chloride, boop, 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 58.45 grams per mole, in case I need that. Adopts a unit cell where the chloride ions form an FCC type structure, boop, 4 atoms per cell. And if the radius. Okay, so radius we'll deal with later. Oh, by the way, notice, and I pulled these off of Wikipedia. It's a very mature site for science information, so pretty reputable. Notice that the sodium ions are smaller than the chloride ions, and so unless they're in some sort of very, very different location in terms of up or down in the periodic table, positive ions are smaller than negative ions because of their proton to electron ratio. There's more protons sucking that cloud in. Now, I didn't draw in the sodiums. I'm going to do that next. What happens with an ionic unit cell is that the anions, the negative ions, are bigger and they adopt a sort of unit cell, could be anything, and the positive ions will fit in there. It's a little Na plus. There's another little Na plus, and then a little Na plus. And you know what? I'm having a hard time drawing it right. But that brings up a good point. What happens in ionic unit cells is the ratio of the radii would have to be perfect for everything to fit perfect. And so you see where I drew this and things aren't touching. Well, there's two ways we could solve this problem, but we're going to need a mass and we're going to need a volume, just like all the other ones we've done. And it's pretty easy to see that the phone's ringing. Hello? Hello?
Hi, this is Matt calling from Starlight TV Services.
Good. I'm talking about sodium chloride unit cells. Could you call back later?
Okay, have a good day.
Okay, you too. Bye. Sorry about that. Okay, I'm back. So here's the thing, folks. We need the mass. That's going to be easy. It's going to be the mass of a unit cell is going to be 4. Now, this is face-centered cubic unit cell, so there's 4 chlorides, and trust me, because there's a 1:1 ratio, there's gotta be 4 sodiums. So what will happen is this will be like a face-centered cubic unit cell, and what will happen here is that these are different kinds of atoms we'll talk about later called edge atoms. That's actually 1/4 of an atom, and so you'll have like 12 of those. That would be worth 3 atoms. And then inside hiding is a body atom, and that would give you another atom. So trust me, there's 4 sodiums, 4 Na pluses, and 4 chlorides. And if you want to just add them together, 4 NaCls. So once again, it's very much like the typical unit cell problem. We have some sort of multiple of number of atoms in the unit cell. So now, volume, you got 2 strategies, and there's error with both. Because like I said, not all these are always touching perfectly. We could do our 4R thing right there. That's a radius, 2 radii, and then another radii, 4R, just like face-centered cubic unit cell. Or that's a radius of a chloride ion to get to that point right there. There's 2R of a sodium, and there's another radius of a chloride. I'm going to do that just for variety. So this would be, according to the given information, 167 picometers. This would be 167 picometers, and this would be 2 times 116. And you see, I might not have drawn it perfectly, and maybe that's why the way I drew it isn't exactly all that accurate, and there's a lot more complexity to these things. This would be 232 picometers. So doing some higher math, L would be 167 plus 167 plus 566 picometers. Remember, volume is L cubed, and that's our mission. So what do you want to work on next? I say we do the mass first, and then we do the volume next. And it's the same old song and dance here. So let's go ahead and say 58.45 grams NaCl in 1 mole. And then let's go ahead and we'll say that, use Avogadro's number, 1 mole, 6.02 times 10 to the 23 atoms, 4 atoms, unit cell. And we're going to get a really, really small number, which we should. And by the way, you notice I happen to, you could break this out and do the 4 sodiums and the 4 chlorides together, but you're really just kind of making more work for yourself. So I added them together and took that times 4. So times 4 divided by 6.02 times 10 to the 23. And we're getting something that probably looks pretty familiar to you in terms of how big these things are. 3.884 times 10 to the minus 22 grams. That's our mass. Fair enough? Let's go ahead and do our volume. V equals L cubed. Once again, I like to convert it to centimeters first. So let's go ahead and do that. 566 picometers. And I know I may have said this before, but I like my ones on the bottom, because I like to be able to just combine powers of 10. So you got to remember that there's 10 to the minus 12 meters in a picometer. And if you get really good at this, you'll be able to convert in one step and know that there's 10 to the minus 10 of a centimeter in a picometer, but I do it in 2 steps. 1 meter, 10 to the 2 centimeters. That would be 566 times 10 to the minus 10 centimeters, also known as, more properly, 5.66 times 10 to the minus 8 centimeters. That is L. V is length times width times height, or in the world of cubes, is L cubed. So 5.66 times 10 to the minus 8 cubed. Once again, I actually have a cube button on my calculator. It is right there. I got to use the second function. So just to give some variety here, which you really need after these things. But we're almost done with density problems. I'm going to go ahead and hit the second button and hit the cube button. 1.8132 times 10 to the minus 22 And I have wonderful news for you, folks. We're going to get lucky again with the powers of 10 not being a pain. 3.884 times 10 to the minus 22 grams. 1.8132 times 10 to the minus 22 grams. Centimeters cubed. Bang, bang. It ends up being whatever 3.884 divided by 1.8132 is. 2.142. 2.142. You know, if I was really going to be complete, I would, first of all, I'd be every digit, everything we've been given was in 3 digits. So I'm going to call it 2.14. That sounds a little low to me. I forget the density of salt, but I do know that at least it doesn't look weird to me. You know it would look weird if I had something like less than 1. Because if you ever taken salt and put it in water, does it sink or float? It sinks, my friends. I did that just yesterday. I brined some potatoes and I poured some salt into water and it went to the bottom. So at least I feel good about the fact that this is a realistic density. Now, why would I be off from the literature value? Remember I said there's a little bit of error with these things. These might not be perfectly touching. And you know, you even have that, you don't have that as much with metallic crystals as you do with ionic, because you got this ratio of sizes. Look, that doesn't look like bigger the length than what I drew, but remember I'm just drawing this freehand. And so I'll show you a figure that's better drawn of an NaCl crystal right now. And then we're going to move on to something else. Hey folks, this is what we call in science a box. And what I did is I drew on it with a Sharpie. This is kind of like the sodium chloride unit cell. This is a box I had sitting around that is it's basically a cube. And you see these would be the chlorides. Here's a face atom. I wrote 1/2 on there because this has been bisected and it's going to be shared between that and a neighboring unit cell. Now this really blows your mind, but this corner atom, corners as we talk, that's being shared by 8 different unit cells. Maybe it's easier to see. This is called an edge atom. We haven't talked about an edge atom yet, but that's a quarter. It's been bisected once, twice. It'd be being shared with a unit cell up here, and a unit cell over here, and a unit cell down there, 4 different unit cells. So, you know, but don't really sweat it too much if you're having a tough time with this. It's tough here, and actually here, I'm going to demonstrate further. Here's how you can prove to yourself all the different kinds of atoms, okay? No, it's not going to get violent. Well, unless you're a tomato. It's going to be quite violent for this tomato. That's like a body atom. And so that would be a body atom. And then if I had a face atom, that would be like if I did this. I'm going to bisect it once. Always bisect your atoms with a serrated knife to get through the skin. There you go. That's a face atom. These edge atoms that I was talking about right there would be if it got bisected twice. That's a quarter of an atom. Oh man, a corner. Can I get away with a corner? See how good my knife skills are, yeah. That's a corner atom right there. So if you were to take this cat right here and go, whoosh, that's right there. And then finally, after you're done, I like to take my face atoms and sprinkle them with some salt right in their face. All right, let's talk about the number of atoms in a unit cell next. All right, folks, I'm back on it with the tomatoes, and I just want to kind of really hammer home one more point, and then you're going to take a little quiz here at the end of this concept, and this is the number of atoms per unit cell. So what happens is, with ionic compounds, the ratio in the formula, now that's cesium, that's in group 1, and you know that this is in group 7 chloride, and those should combine back to Gen Chem 1 in a 1-to-1 ratio. So I'm going to take these, this is sort of like what the cesium chloride structure looks like, is the cesiums are, I should say, the chlorides are a little bit bigger. How come they're not as outrageously bigger? This would be actually, we're going to call that a cesium. We're going to call these cesiums, make them a little different color. And they're slightly smaller, but not tremendously, because cesium is really far down on the periodic table. And the way cesium chloride looks is you got sort of like body-centered cubic. So you've got these chlorides, and then you got chlorides on top like that. And that's the sort of shape they make with, looks like body-centered cubic, doesn't it? But there's a couple concepts I want to talk about. First of all, the number of atoms per unit cell should be consistent with the formula. So you see that there's 4 corners, and that would be 1 equivalent atom for four corners. So this would be 1/8 times 8 equals 1. This would be a body atom. That cesium is 1 body. So the number of atoms per unit cell should reflect. It's 1-to-1, just like in the formula. There's another thing called coordination number, and I'm going to try to demonstrate it here with something that's 1-to-1. And folks, with tomatoes, that's all I can really get away with, is something simple like this. Coordination number is the number of nearest neighbors . So if I was to look at that cesium, excuse me, I would be able to count how many chlorides were around it. There are 1, 2, 3, 4, 5, 6, 7, 8. And so the coordination number of cesium would be 8. This is going to take a little bit more imagination from you. But let's go and say, what if this was infinite? And you had, of course, every other layer repeating, and you had more cesiums. If you were to be a chloride, you would find that there are also 8 cesiums around it. And so this should hold the same ratio. Now what if it was something 2-to-1, like water? Well, you're going to find out that in the structure of water, which we talked about when we talked about phase diagrams, in ice, solid water, you're going to find that the coordination number of oxygen, which is the number of hydrogens around it, is double that of hydrogen, because there's 2-to-1 ratio. So let's do a little bit of a quiz next, and that's how we're going to end this particular video. Let's go and take a pop quiz, and we're going to take some structures, and I'll tell you even what they are as we go along. But we're going to have you guess which one is which atom. Now remember, there's a size thing that in the model should be able to help you out. And how many of each atoms are there per cell? And then we're going to ask you another question about the coordination number, like how many nearest neighbors are there around each. And by the way, when I'm talking about the coordination number of something, I'm talking about how many other things are around it. So the coordination number of cesium is how many chlorides are around it, and the coordination number of chloride or how many cesiums are around it. So as we bid solids adieu, I got one more pop quiz from you from images that I have legally obtained from the interwebs. Till then, see you guys later. Hang in there and do this 1 or 2 minute pop quiz. Feel free to pause the video if you need to glance at the models more. But until then, bye.